Okay, today we are going to talk about spherical coordinates. This is another way of representing points in 3 dimensions. So, let's imagine the Earth here, and these pictures are all on the notes too, or most of them are, so if you want to go by that instead, or if you want to follow along. We have the Earth here, and this line represents the axis of rotation, which is usually about 23 degrees from vertical. Or usually, it's always. So, we can represent a point on the surface by two values here, latitude and longitude. So, we'll do theta first, is latitude. Or, no, longitude. I get that backwards all the time. Theta would be longitude because it will represent east, west, north, south. So what this means is we say, so let's say this is the prime meridian here. Goes through Greenwich, England, and at the exact other side of it would be the international date line. That's out in the Pacific Ocean. So what happens is we start here at the prime meridian, theta is 0. At the international date line, theta would be 180 degrees or pi radians, and we usually use radians in this class. And so go around in this direction going eastward, and as we go eastward on the globe, that represents an increased theta. Because if you could just look straight from above and you would just see the equator, it would look like this. So in the xy plane, theta is the same theta we've been dealing with this whole time. It is the distance around the unit circle. It's just now we're saying it doesn't have to be flat on the ground. Well, I guess we've said that all along. It's kind of like with cylinders, but we're going around in that counterclockwise direction. But we also want to have a way of representing the latitude, and that we usually use the letter phi. I say usually, the textbook points out that some physicists, some physics text switch these, but for us, phi is latitude and theta is longitude. So phi would represent the distance downward. This one we have to be a little careful about how we represent it. It is phi equals 0 is the North Pole. And then the South Pole is half a circle around, so you say phi equals 180 degrees, or pi radians, is the South Pole. So the equator would be pi over 2 radians. So this is easy to get disoriented which way is which, because, again, like most of our conventions, they're kind of arbitrary. Why do we say North Pole is 0 and not the South Pole? Because we do. It's just the way we've agreed to say it. So 0 degrees is straight up, and 180 degrees is straight down, 90 degrees is horizontal, and we don't go past there. I know it might seem tempting to go all the way around, but if you think it over, that would be double counting. If we were to go around here, well, there'd be no point, because if we have a point, like say, this is theta and this is phi, well, we can just go around another half theta instead of having to go all the way around here. They get to the same point. So the point there is that we are going to limit our angles again, just like we did in the previous cases, so that every point has a unique representation. So we will say theta is between 0 and 2 pi. I'm not saying equal because 0 and 2 pi would be the same thing. And phi is between 0 and pi. Now that's enough to give both, they give both latitude and longitude, so they give any point on the surface of the Earth, or any sphere, really. I'm saying the Earth because it's convenient. On actual globes, they might, well, they'd have north and south, east and west. Those are kind of like positive and negative, but we're keeping it simple with just these limits so that we don't double count anything. Okay, so we are talking about three-dimensional space. We have a sphere here, and that gives us everything on the surface, but what if we want to point on the inside of it, or on the outside? Give a little depth illusion to that. There we go. We can have smaller or larger spheres. So if we knew a point on the surface here, we could follow it out any distance to get another point in space that's not on that surface. And so that distance from the center, from the origin 0, 0, 0, is called rho. And it's always greater than or equal to 0. So it's the three-dimensional equivalent of radius. When we use little r, that represented radius in the xy plane. But now we're including the z plane as well. So we're in 3 dimensions, so we are going to use rho is greater than or equal to 0. It is the distance from the center. All right, so with that said, we now know how to, well, we should explore what it looks like if we fix some of these values, like we did in the last case. So, what if rho is some constant capital R? Well, that means it's a set of all points whose distance from the origin in 3D are the same. Hopefully, it occurs to you that this is the definition of a sphere. So if this is R here, and this is also R, or 0, R, 0, I suppose, 0, 0, R, and R, 0, 0. And so we get a sphere. Sphere is all the points that are the constant distance from R. And you can shift it and such like we would with any other. But I want to point out what we're saying, that if we were to write this, say, what are all the points, say, x, y, z, whose distance from the center is R? That would mean square root of x squared plus y squared plus z squared would have to always equal constant R. That's ugly. That's a lot of square roots. But in spherical, it's just a nice simple statement, rho equals R. What about the others? Well, what about theta equals a constant c? Well, what that would look like we would have theta would be the angle going out from x like this. So let's say this angle here is theta. It would be then all the points along this line. So again, I find these are particularly hard to draw, but it'll give you a half plane. Again, because we said that theta can be a, what they're trying to say. Yeah, it doesn't go backwards, so I should probably erase that part. Theta points outward. Going the other way would be c plus pi. So it's actually not a full plane, but just a half plane. So I want you to imagine there's this line in the ground, or this ray, I suppose, because it only goes one direction, and a plane or a sheet of metal or such shooting up and also shooting down. Okay, so that's a constant theta. It gives you this half plane. What about if phi is constant? So phi equals c. Well, if c is between 0 and pi over 2, actually I should say if c were exactly 0, if we were pointing straight up, that would be just a ray. Let me see if I can explain this a little more clearly. If c equals 0, that means we're on the z-axis. We're pointing straight up. So that's not that interesting. Let's not do that. Oh, I deleted too much. Let me fix that. All right, so if c is between 0 and pi halves, well, pi halves means we're in the xy plane. And in that case, the rho would be the same as r, and we'd really be dealing with polar coordinates. So pi halves would mean we are on the ground, the xy plane. All right, what if it's in between? Well, then what we get is a cone. So we get this angle is c, it's phi equals c. But theta is allowed to go the full 360 degrees to sweep out an entire cone. And rho is also allowed to be anything, meaning we can go out as far or as near as we want on this cone. Whereas if instead we had phi is constant and it was greater than pi halves but less than pi, that would be a cone that opens downward. That's underneath the xy plane. In fact, let me go use some dotted lines here to make that a little. Okay. By the way, that reminds me that I want to clarify something from the last lecture when I was talking about whether the cones were a cone or a double cone. I think if I said z squared equals r squared, that's a double cone. Because it could be positive or negative. But then if I take the square roots on both sides, I have to add in a plus or minus square root of r to get both of them. So if I just said z equals r, that means they have to be the same sign. And since r can only be positive, that would throw out the bottom one. So I had a little confusion because they were both in the book and I didn't want to stop the video and look it up, but that's the explanation there. Okay, so our next thing, we need to know how to convert. Because the whole point of this usually is we see a problem in XYZ and we think this might be easier if it were in a new coordinate system. So this is a little tricky, but I am going to try to show you where some of this comes from. Oh no, wait, I've already written this down. Let me scroll down to where I thought I had this written down already. Oh, I must have accidentally deleted it. Oh well. Alright, so what we get is, let's draw this again. Here's X, here's Y, and here's Z. Let me straighten out that Y. That Y's a little jagged, a little wobbly. There we go. Okay, so I'm going to draw, we're going to try to go from X, Y, Z and figure out what the new points are. So let's call that P. So here's a point, P equals X, Y, Z. And now I'm going to say P prime will be X, Y, and 0. So let's project this P downward to about here. That's P prime. Now, P prime is in the XY plane, so we can define it using theta and r. And I know where r is not where we want to end up, but we remember what it means. It's how far we are if we're staying in the XY plane. So let's do this. This gives us a line segment there of length r. And I want to emphasize there's a right angle here. And maybe it doesn't look like that, but r, or this red ray, is in the XY plane, and this blue ray is coming directly out of it, straight up. So that is a right angle. Now we'll draw theta here. I don't know if I actually, no, I do need theta eventually. So we know that x equals r cosine of theta, and y equals r sine of theta. And we'll substitute out those r's when we get a chance. Now, the ray here from the origin up to the actual P, that has a length of rho. Because that's how we define rho. It's the distance, straight line distance from the origin to the point. And so you're picturing this triangle out in space here, rho, r, and I guess this part has length z, because it's straight up to the point x, y, z. Well, a couple things we notice here. Here's a right angle, so this triangle is a right triangle. We can use the Pythagorean theorem. And that would say that, let's see, if this is the right angle, then rho is the hypotenuse. So rho squared equals r squared plus z squared. But r squared, from our work with polar coordinates, is x squared plus y squared plus z squared. So there's our first identity, which is what we probably expected. It's just another version of the distance formula. It is the distance formula in 3D, really. And it's very similar to the r formula from 2D. So that would be the first identity worth writing down. Now, what else do we know? Well, this angle here is phi. If we think back to high school geometry. There's the alternate interior angle here. This angle is also phi. So we see another relationship that z, rho is the hypotenuse, z is adjacent to the angle phi, so we can get z equals rho cosine phi. Because right here, if I put this triangle in 2 dimensions, let's not do it like that. Let's do it the other way. Keep the orientation the same. If I were to take this triangle out of the 3D plane and just look at it by itself, it would look like this. Here's phi. Here's a right angle. I don't know what this other angle is, but I don't think we really need it. Here's z, rho, and r. So we can see z is rho cosine of phi. That x was not part of the formula. That was part of the graph over here. So write this one down too. Z equals rho cosine phi. That is a conversion. It doesn't have anything but rho, phi, and theta would be okay too, but we don't need it for this one. Now what about x? What about r? Well, r, we can see from this, r equals rho sine of phi. Because phi is opposite from r, so we use the sine function. Then plug that into these equations, and we get x is rho sine phi cosine theta, and y is rho sine phi sine theta. So I'm boxing the formulas you need. If you didn't follow all that, it was geometry and trigonometry, but trying to do that in 3D, I understand I might have lost some of you. And if that was too much, just write down these formulas in the boxes and commit them to memory. They are the ones that you need. Now, there's one other, well, no, we'll save the other issue next. Let's do some conversions first before we go on to that. So, let's do a couple examples here. Rho theta phi is 2 pi fourths pi thirds. Let's try to change those into x, y, z. How would we do that? Well, we can really just do it by plugging into the formulas. X would be 2 sine pi thirds cosine pi fourths. And you may have noticed that the x and y, they both have the cosine theta and sine theta the same as they did back in 2 dimensions. So that becomes 2 times root 3 over 2 times root 2 over 2. So that gives us root 6 over 2 is x. Y is 2 sine pi thirds sine pi fourths. But sine pi fourths and cosine pi fourths are the same thing, so we'll end up with root 6 over 2. So this is the case because the angle theta is pi fourths. That gives us the x and y being the same thing. And then z is rho cosine of phi, so 2 cosine pi over 3 is 1. So, simple enough. What about going back the other way? See, we have x, y, z equals to 0, 2 root 3, negative 2. And we want to change them into rho theta phi. Well, we can use the distance formula. Rho is the square root of 0 plus 2 root 3 squared plus negative 2 squared. I guess I can put squared on the 0 too if it makes you feel better. Doesn't really matter. This becomes 4 times 3 is 12 plus 4, so that's root 16 or 4. All right, so rho is 4. Now, we can use our formulas that we have. We just have to sort of solve them backwards. Okay, z equals rho cosine of phi. So then negative 2 would equal 4 cosine phi, meaning cosine phi is negative 1/2, and therefore phi is 2 pi over 3. That's trig there. 60 degrees. 60 degrees gives you cosine is 1/2. So 120 degrees, same reference angle, gives you cosine of negative 1/2. That's just a little bit of trigonometry, but I thought I'd... Okay, so we've got two of the coordinates now. Rho is 4. Phi is 2 pi over 3. This is probably the correct order to go in. Rho is the easiest. Then you use the z to solve out for phi. And then use either the x or y. X is 0. So, actually, because x is 0, it probably... Well, maybe. Let's try x. It's 0, so it might help. X is rho cosine theta sine phi. That's the formula. So 0 equals 4 times cosine of theta times sine of 2 pi over 3, which is sine of 2 pi over 3 is negative 1/2, so we get negative 2 cosine of theta. So if that's the case, then it's clear that it must be cosine of theta is 0. So what angle has a cosine of 0? Well, we've actually got two options, don't we? We've got pi halves or 3 pi halves. So like last time, we have to use what we know here based on the... Well, y is positive. That's what I'm saying. Since y is positive, that means it must be pi halves. You know, we are in the xy plane. The projection would be up here somewhere. So since y is positive, it's positive pi halves. So that's our answer. 4, comma, pi halves, comma, 2 pi over 3. Okay, so that's conversion. Going from spherical to rectangular is probably easier than going from rectangular to spherical. You could probably write formulas solved out in terms of x, y, z, but I think that's harder than it's worth. Too much work. But there is another issue when we're doing integrals, and that's how do we convert dv? As we've seen with polar and cylindrical, we have an extra little multiplier that has to come along. And so if you're looking at the notes, there is a picture that looks really weird. It's like this or it's like some sort of wedge that's in 3D. And that, frankly, I find this difficult to deal with. And I thought about trying to work my way through the whole thing and show it to you. And that turned out to be pretty complicated. Li, length I, width j, height k gives you a volume ijk, because it's approximately the same as a box if they're all the same. And so a spherical prism would be something that is of this wedge shape so that the endpoints are all constants like before. But what is the dv? And I've decided I'm not even going to bother showing you. I'm just going to jump to the answer. dV is rho squared sine phi. D rho, d phi, d theta. So, what are we saying? We're saying if you're changing into polar or cylindrical, you need to multiply by an extra r. Well, if you're changing to spherical, you need to multiply by this whole other thing, rho squared sine phi. And the best justification I can give, well, I give you for the order of it, which is that if there are meters here, this is meter squared, multiply together you get meter cubed, because everything else is an angle and those aren't true units. But actually, next chapter we will show another way of changing coordinates, and at that point I may be able to prove to you why this works. For now, I would say just memorize this. When you're changing to spherical, you need to multiply by rho squared sine of phi. And so it'll be best if you just take my word for that for now, and maybe we can explore it more later. So let's do a couple examples, two examples, yeah, of how to do some of these integrals. All right, so evaluate the triple integral across the box B of e to the x squared plus y squared plus z squared to the 3/2. So it's a power to another power, dv, where b is the unit ball. So it's a set of all points or vectors. I'm not sure which is the probably should be point. Set of all x, y, z whose length is less than or equal to 1. Okay, now trying to do this in x, y, z looks bad because we got exponential of x squared, and I had mentioned before that an exponential of a square, that's a really hard function to deal with directly. In fact, I don't think it's possible to do this one in rectangular coordinates. You could try, but you'd try u sub and it would just fail. But I look at this and I say x squared plus y squared plus z squared, that's the same as rho squared. This is shouting to me I should probably use spherical. So this would equal the triple integral of e to the, this is, if you want to do a little sidebar here, e to the rho squared to the 3/2, or no, hold on a second. Sorry, the 3/2 is part of the e. This is really precise. E to the rho squared to the 3/2. So those powers get multiplied and it becomes e to the rho cubed. It's a stack of powers. This is tricky. Sometimes I like to write exponential of x squared plus y squared plus z squared to the 3/2. That's one way of doing it when the powers get out of hand. You can just write exp, and it's understood everything in there is a power of e. Anyway, so this becomes e to the rho cubed. Now, since we're converting into spherical, we need to multiply by rho squared sine phi d rho d phi d theta. It's the unit ball, so since it says it needs to be less than or equal to 1, we are including the interior of the ball, not just the surface, everything inside it. So that means rho needs to go from 0 to 1. Phi goes from 0 to pi, and theta goes from 0 to 2 pi, because like we said, if we want to include everything in a sphere, theta goes from 0 to 2 pi, but phi only goes from 0 to pi. So I think it would be a common mistake if you made them both 2 pi. Let's not do that. Okay, this is factorable. This is the rho part. This is the phi part. This is the theta part. I guess this goes here and this goes there. So we'll factor this into 3 pieces. 0 to 2 pi d theta 0 to pi sine phi d phi, and 0 to 1 e to the rho cubed times rho squared d rho. Well, now, this is it. This last one on the right, that's a u sub. We want to say u is rho cubed, so du is 3 rho squared d rho. So you see what happened, that rho squared we had to bring in actually is what saved us, because it gave us our du. We need to put a 3 here and a 1/3 here. Or, if you want to solve for it as d rho is du over 3 rho squared, same effect. This is just how I learned how to do it. Okay, so we get 1/3, and then this would just be 2 pi, because it's a perfect integral, it's just d theta. This is from 0 to pi negative cosine phi. And this one is integral of e to the u du. What is u doing? Let's see. Rho went from 0 to 1. U is rho cubed. I guess then it also goes from 0 to 1. 0 cubed is 0. 1 cubed is 1. So that becomes 2 pi over 3 times negative cosine phi minus negative, so plus cosine 0 times from 0 to 1 e to the u. So that's 2 pi over 3 times 2, because cosine pi is negative 1, so it's 1 plus 1, times e to the 1 minus e to the 0. Be careful of that. This is a case where the 0 can't be ignored. So we get 4 pi over 3 e minus 1. That's our answer. All right, I've got one more on the notes that I want to do. So let's see. We want to find volume of solid above the cone z equals square root of x squared plus y squared, and below the sphere x squared plus y squared plus z squared equals z. Now, it's not immediately obvious that that is a sphere, but we can work it out. Let's see. All right. So what we're essentially getting is like an ice cream cone situation. We've got a cone here and then a sphere. And so we want the part that's above the cone but below the sphere. So that's everything that fills in the ice cream cone. So how do we do this? Well, we want to do a triple integral across E, I'll call E the space, of the 1 function dv. So I want to convert these to spherical coordinates because I see this x squared plus y squared plus z squared is z. And I think there's some homework problems that'll be like, write it in cylindrical and polar and, or not cylinder, and rectangular and spherical, and write in every different way and to decide which one's easiest. And so if we were doing this in rectangular coordinates, we would say we're above this. So it would be square root of x squared plus y squared is less than or equal to z, which is less than or equal to x squared plus y squared plus z squared. But start doing this with z going from there to there, and then y would have to go from like 1 minus square root of x squared or something like that. You know, square root of 1 minus x squared. It's ugly, right? This is, again, a case where we've got all these squares, so it's worth thinking maybe spherical would be best. Maybe cylindrical would be best. On a test, I would not insist you do it one way or the other, and it may be just a matter of taste which one is best. But we're going to do sphere this time because that's what we're learning about. So I want to try to convert these boundaries. This is the actual definition of the region. It says we're above square root of x squared plus y squared and below x squared plus y squared plus z squared. So so this is everything if we can write this in the correct way. So let's see how we do that. All right, let's do the cone first. So on the cone, we have z equals square root of x squared plus y squared. I know it's tempting to say that's r squared, but we're trying to do spherical coordinates, so r won't help us. So let's instead plug in the formulas for x and y. So we get rho cosine phi equals square root of rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. All right, so we want to simplify where we can. This right-hand side, well, we will factor out everything that can be factored. They both have a rho squared and a sine squared phi. So let's write it as rho squared sine squared phi with cosine squared theta plus sine squared theta. Well, that's 1. So that part's gone. So we just have a square root of a square, which would make it rho sine phi. Technically, there's an absolute value in there, but we're insisting rho be positive anyway, and so I don't think we need to worry about that. I guess phi, sine phi being negative would mean the cone would be below the xy plane, but just from the way it's described, we're saying we're above the cone, and that cone is positive. So let me restate what I'm saying here. I'm saying if z equals r, we said that's a cone that goes up, so we know phi has to be positive because it's above the xy plane. But we're not actually dealing with r, but it's still there. Okay, so this tells us we have rho cosine phi equals rho sine phi. So we can, let's see, I think we can divide out the rows as long as they're not 0, which, well, 0 is the end point. Sorry, divide by cosine on both sides here, and we get 1 equals tangent of phi. And so from your unit circle, what angle is the tangent of phi? It is pi over 4. So I want to emphasize what we've said here. We've said this cone that we started with is entirely represented by the expression phi equals pi over 4. If phi is pi over 4, we're on the cone. And if we're on the cone, then phi is pi over 4. They mean the exact same thing. So we don't need any of this. We can just replace it by saying phi equals pi over 4. And if you'll remember what we said phi always comes from above. So if the z-axis is here in the middle, that means phi, if we're above the cone, could be anywhere between 0 and pi over 4. So that is what we've just found. We've said that 0 is less than or equal to phi is less than or equal to pi over 4. Okay, what about the other piece? Well, the other piece was the sphere rho squared equals rho cosine of phi. I just took this equation here and I made our substitution. The left side is rho squared, the right side is rho cosine phi. Again, we can divide out the rho. So we'll get rho equals cosine of phi. Well, that's also an expression. That does what we need. If we are in this cone and under the sphere, saying that every point in here, if we were to pick a direction and follow it out, rho can be any distance. Rho is the distance we are along this ray. When we hit the edge, rho equals cosine of phi. That's what this is saying. The sphere itself, the boundary of it, is expressed by this equation, rho equals cosine phi. So we can write this as saying rho goes for everything between 0 and cosine of phi. Whatever cosine phi is. Since it's a unit circle, that means if it went straight up, rho would equal 1. But if it went sideways, it might stop before we get that far. Okay, so those two expressions are everything. You'll notice we don't have any restrictions on theta. So if that's the case, we expect theta to be everything. And, you know, this cone goes all the way around, so that makes sense. Theta is 0 to 2 pi. So this gives us a nice polar, or not polar, a spherical prism, I guess you might call it, meaning that all the endpoints are going to be constant. We will have the integral, triple integral. Now it said 1 dv. Since we're changing to spherical, we need to bring in that rho squared sine of phi multiplier. Then we have d rho, d phi, d theta. And we said rho goes from 0 to cosine of phi. Oh, I take it back. This is not a spherical prism because this cosine phi is not constant. So my mistake. I misspoke a minute ago. But, okay, phi goes from 0 to pi fourths. And then theta goes from 0 to 2 pi. Okay, so since this is not a prism, since the first integral has a function as one of its bounds, we can't rearrange it. We need to do that one first. So 0 to 2 pi, 0 to pi fourths, and then we have, we're doing the integral of rho. Yeah. So that becomes the evaluate from rho is 0 to rho is cosine phi of 1/3 rho to the third sine phi d phi d theta. Well, then that gives us 0 to pi, 0 to pi fourths. Now let's plug in cosine phi and 0. The 0 term will go away. So it'll be 1/3 cosine cubed phi sine phi d theta. Okay, I'm gonna erase all this, whatever that's from earlier. All right, this phi integral is a u sub. We can say u is cosine of phi, and du is negative sine phi d phi. So I will put a negative there, negative out front for balance, and so I get the negative integral from 0 to 2 pi d theta. I'm factoring again. And the integral from 0 to pi fourths of 1/3 u to the third du. I made a mistake here. We need to change those limits, don't we? All right. Phi went from 0 to pi 4, so let's plug those in to get what u is. Cosine of 0 is 1. Cosine of pi fourths is root 2 over 2. Root 2 over 2 is less than 1, so this is an upside down integral, so I can switch it and get rid of that negative sign. Become integral from 0 to 2 pi d theta, integral from root 2 over 2 to 1. Let's pull that 1/3 out there. U cubed. So that'll be 1/3 0 to 2 pi theta, and from root 2 over 2 to 1 of 1/4 u to the fourth. And then we finish this off. It's then, let's see, 2 pi over 3 times, let's see, 1/4 minus, I'm plugging in 1 for u, so I get 1. Plugging in root 2 over 2. Root 2 over 2 squared is 1/2, so 1/4, so 1 over 16. And now this is one of these cases where you hope you got it right, because my notes don't, I did it in a different order. Times, yes, 1/4 is 4 over 16, so this is 3 over 16, which becomes pi over 8. That's right. Okay, so those are the basics, and we will, of course, have plenty of time to do practice. So I will see you then.